Hi friends, today we are going to discuss on two topics which are very useful for site engineers. First one regarding what are the lapping zones in beam, and second one is this is quite common question, why usually shorter side reinforcement placed first in site then longer side reinforcement for a slab. The first question comes to in our mind, what why we need to the lap for a beam. Usually our beams, continuous beams exceeds the spans more than 12 meters. The average length available in the market for a steel bar is maximum is 12 meter only. But our beams exceeds usual span is more than 12 meter only. I am talking about overall span, not the span between the supports. Coming to the our first question, what are the lapping zones for a beam? Here I have considered a beam between two columns and whose span is usually 8 meters. Generally, we have the perception bottom reinforcement. We generally don't need to lap at the center. Usually, we will think there is a maximum bending moment is going to occur at the center. And top reinforcement, we will always need to do lap at the center. Why we need to do like that? The reason behind that, generally, there are two types of loadings. One is the gravity loading, and another one is the lateral loading. If I consider one a portal frame, which is subjected to the uniformly distributed load. For example, this is like a gravity loading case. Whenever there is a gravity loading case, as usual, there is a bending moment drawing is going to get like this. Usually at the supports, there is a hogging moment, and at the center, there is a sagging moment. In our minds, it only comes always. Based on this drawing, the bending moment is maximum at the center for sagging moment. So we don't need to lap the main reinforcement at the center. This is only true only if only there is acting of the gravity loading. But whenever there is action of the lateral load on the same beam, we are going to have the maximum moment at the supports. By believing our only gravity loading exists, we are going to do lap at the supports. If there is action of the lateral load, it is going to get failed. Whenever there is action of lateral load, your bending moment is going to drastically increase at the supports. That's why our code IS 13920 2016 proposes the longitudinal bonds shall not be provided within a joint and within a distance of 2D from joint face and within the quarter length of the member where flexural yielding may generally occurs. Within the joint, if we're going to do lapping, there may be two problems. One is the congested of the reinforcement, and another one is there is going to occurrence of the huge bending moment whenever there is action of the lateral loading. And usually, where is going to occur in the flexural yielding? Flexural yielding usually occurs wherever there is a maximum bending moment. At whenever there is a gravity loading, the flexural yielding usually going to occurs at the center of the beam. That's why our code proposes logically it should not be at a distance of 2D from the face of the column. If I take 2D from the face of the column, the maximum bending moment is reduced. And wherever and it should not be occur at the L by fourth from on either sides of the maximum bending moment where flexural yielding usually occurs. Means if I take the 8 meter span from the center L by 4 on either side, L by 4 means 2 meters. From here 2 meter, from here 2 meter. The reinforcement should not be lapped under the gravity loading case. And whenever there is a lateral loading, we should not do lap from the at the face from the face of the column 2D. From face here 2D, here 2D. And we are going to do the lap only whatever the portion is going to left here. from here 2D and from center to L by 4. From here to here we need to leave 2D and from here to here we leave 2D. From center L by 4, from center L by 4, whatever the portion is going to left. Whatever the portion is going to left, we are here only where I have drawn the circle. Here to from L by 4, here to 2D. Remaining portion we need to do the left. We have to do the lapping. Regarding to the top reinforcement always going to be do lap at the center of the on the center. Usually from center to L by 3, L by 6, L by 6. The reason is quite obvious here. If you look at the gravity loading case, there is no bending moment at the center of the on the top span. It is usually having always compression only. When coming to the earthquake loading or lateral loading case, also there is no moment at the center. There is almost zero moment. From 1 and 2 gravity loading and lateral loading cases, if you observe, there is no tension is going to occur at the top of the beam. At the top at center of the beam. Usually there is going to have the compression. Therefore, when we are going to do the lap at L by 3 of the center of the beam for the top reinforcement. Regarding to our second question, why usually shorter side reinforcement placed first inside then longer side beam for a slab? For this, I have considered the basic concept is moment. M is equal K theta is nothing but it all depends upon the stiffness of the member. Stiffness is generally the amount of moment or load required to produce the unit deformation or unit rotation. Generally, if we consider stiffness, any stiffness, if you take the axial stiffness A by L, bending stiffness EI by L cube, torsional stiffness GJ by L cube, any stiffness, if you can take in, it is always inversely proportional to the span of the member. Our, if our span is less, it's automatically stiffness is going to go increases. Whenever stiffness is going to increases, in order to produce the unit rotation or unit deformation, it is going to absorb more moment. If we consider a 2 meter and 3 meter span, 2 meter obviously its length is less. Automatically its length is going to get decreased, its stiffness is going to increase. In order to produce the unit deformation or unit rotation, it is going to get absorb more moment. More moment, whenever it is going to absorb more moment, in order to resist to that moment, it also need to have the more moment of resistance. From RCC, we generally study the basic equation in order to writing moment of resistance equation 0.87 Fy AST into D minus 0.42 XU. I hope all of you know this formula. If you write XU in terms of something constant K into D, here moment of resistance is directly depends upon on effective depth. If our effective depth is going to increase, our moment of resistance is going to increase. Whenever span is less, stiffness is going to increase. Whenever stiffness is increased, it will absorb the more moment in order to produce the unit rotation. In order to resist that, we need to increase the effective depth. Whenever we increase effective depth, automatically is going to moment of resistance is going to increase. Coming to effective depth, in order to increase the effective depth, either we need to place, if I place the bar which is parallel to shorter span first, the effective depth is going to increases. Why? Because effective depth in this case is total depth minus clear cover minus half of the dia, which is parallel to the main reinforcement, which is parallel to 2 meters. If I place the bar parallel to the longer sides first, then our effective depth is equal to total depth minus clear cover minus dia of the bar, which is parallel to the 3 meters, which is parallel to 3 meter minus half of the dia, which is parallel to 2 meter. If I place longer bar first, then our effective depth value is going to come less. When your effective depth value is going to come less, then your moment of resistance, you are getting less. In order to have more moment of resistance, we need to place the bar parallel to the shorter sides always first. This is the common logic we are going to always follow inside. This holds good only whenever the support stiffness, whenever our slab supports on at beams, all sides the stiffness is going to get is same, then only this validates. Hope this video is helpful.